What if every particle in the universe was secretly whispering to each other? Imagine a hidden conversation, an invisible thread tying everything together. Stars, galaxies, even the atoms in your body, all connected in ways that defy logic and distance. This isn't science fiction. It's one of the most baffling discoveries in modern physics. Quantum non-locality, the phenomenon where particles influence each other instantly, no matter how far apart they are, challenges everything we thought we knew about reality. Einstein called it spooky action at a distance, dismissing it as impossible. Yet, decades of experiments have proven it's not only real, it's fundamental to how the universe works. Think about that for a moment. Two particles separated by the width of a galaxy can somehow know what the other is doing. Change the spin of one and the other changes too instantaneously, as if time and space don't exist between them. This isn't just about tiny particles in a lab. If non-locality is woven into the fabric of reality, what does that say about us? Are we, on some level, part of this cosmic dance? Could the universe be far more interconnected than we ever dreamed? Today, we're diving into one of the deepest mysteries of existence. We'll explore how quantum non-locality shatters our classical notions of separation, how it might hold the key to understanding consciousness, black holes, even the nature of time itself. Along the way, you'll encounter experiments that bend the mind, theories that blur the line between science and philosophy, and a vision of reality so strange, it'll make you question whether anything is truly separate at all. This isn't just a story about physics, it's about the hidden unity of everything. So let's begin. To understand how this cosmic connection works, we need to start with one of the most famous thought experiments in physics, the EPR paradox, named after Einstein, Podolsky, and Rosen. Picture two particles born from the same quantum event, like twins sharing an invisible bond. These particles become entangled, meaning their properties are linked in a way that defies classical intuition. Here's where it gets wild. If you measure the spin of one particle and find it's up, its entangled partner instantly becomes down, no matter if they're a millimeter apart or separated by the vastness of a galaxy. This phenomenon directly clashes with Einstein's theory of relativity, which states that nothing can travel faster than light. Information should take time to cross space, yet entangled particles seem to communicate instantly, as if the universe has a hidden hotline bypassing the speed limit. Einstein hated this idea, calling it spooky, because it suggested a deeper layer of reality where separation might be an illusion. But here's the kicker: decades of experiments, from labs on Earth to satellites in space, have confirmed this spooky action is real. Take the groundbreaking work of physicist Alain Aspect in the 1980s. His team sent entangled photons flying in opposite directions and measured their properties at the exact same moment. The results: the particles were always perfectly correlated, faster than light could have carried any signal between them. It's as if the universe cheated its own rules, proving that at the quantum level, particles don't care about distance. They're playing by a different set of rules, one where connection doesn't depend on space or time. So what does this mean for our understanding of reality? If entanglement holds true across cosmic scales, it hints at a universe far more unified than we ever imagined. Maybe the stars, planets, and even you aren't truly separate, just different expressions of a deeper, interconnected whole. And if that's the case, the boundaries we take for granted might be nothing more than a trick of perception. But here's the twist: if entanglement defies common sense, how do we know it's not just some hidden variable, some unseen hand guiding the particles behind the scenes? That's exactly what physicist John Stuart Bell set out to investigate in 1964. Bell's theorem wasn't just a hunch, it was a mathematical bombshell that forced physicists to confront an impossible choice. Either the universe allows spooky action at a distance, or reality itself isn't objective. There's no middle ground. Bell's genius was framing quantum weirdness in a way that could be tested. He devised an inequality, a kind of cosmic speed limit that any local hidden variable theory would have to obey. If quantum mechanics was correct, experiments would violate this inequality, proving that particles communicate faster than light or that their properties aren't fixed until we observe them. It was a lose-lose scenario for classical physics, a mathematical proof that reality couldn't be both local and real at the same time. For nearly 2 decades, Bell's theorem remained a theoretical curiosity until Alain Aspect and his team took it to the lab in 1982. Their experiment was sleek, ruthless in its design. They sent entangled photons racing in opposite directions, then measured their polarizations at detectors set at different angles. The kicker: the detectors switched their settings after the photons were already in flight, eliminating any chance of hidden signals sneaking through. The result: Bell's inequality was shattered. The photons correlated in ways no classical theory could explain, as if they were dancing to a tune written outside space and time. Aspect's experiment didn't just confirm quantum mechanics, it tore down the last pillars of local realism, the idea that objects have definite properties and can't influence each other faster than light. Suddenly, the universe looked less like a clockwork machine and more like a vast, shimmering web of instant connections. Even today, refinements of these experiments using quasars billions of light-years apart as cosmic random number generators keep ruling out loopholes, stacking the evidence higher. So what does this mean? If Bell's theorem holds, we're left with a universe where either influences jump across space instantly, or particles don't even have properties until we look at them. Both options rewrite the rules of existence. It's as if reality itself is a conversation, a dynamic interplay where separation is an illusion, and every observation pulls the universe into being. No wonder Einstein was unsettled. This isn't just physics. It's a revelation about the very fabric of being. If particles can stay entangled across a lab bench or even a continent, how far does this cosmic connection really stretch? The answer might rewrite the boundaries of physics itself. In 2017, China's Micius satellite shattered records by beaming entangled photons down to ground stations over 1,200 kilometers apart, a distance so vast the particles had to pass through Earth's turbulent atmosphere without breaking their eerie synchronization. And against all odds they did. The experiment proved entanglement isn't just a delicate lab curiosity, it's robust enough to survive a journey through near space, hinting that the universe might be crisscrossed with invisible quantum threads even between stars. But here's where it gets cosmic. Some theorists speculate that if entanglement can span continents, why not galaxies? The early universe was a hot, dense soup where every particle was jammed together, inevitably entangling in ways that might still linger today. Cosmic inflation, the rapid expansion of the universe right after the Big Bang, could have stretched these quantum links to unimaginable scales. Picture a rubber sheet imprinted with a pattern, then stretched to the size of the observable universe. Those original connections would thin out but never truly snap. If true, entanglement might be woven into the very architecture of spacetime, a relic of when everything was touching. This isn't just poetic speculation. Physicists like Juan Maldacena have proposed that black holes, those cosmic vacuum cleaners, might be connected by quantum tunnels forged from entanglement. And the holographic principle suggests our three-dimensional reality could be a projection of entangled quantum data, stored on a two-dimensional surface at the edge of the universe. Think of it like a cosmic version of a butterfly's wing, tiny, intricate patterns encoding something vast. So what's stopping us from proving entanglement spans the cosmos? For starters, detecting it across interstellar distances would require technology light years beyond our current grasp, literally, but the math doesn't rule it out. And if future telescopes or quantum sensors ever catch whispers of galaxy-spanning entanglement, It would mean the universe isn't just expanding, it's conversing with itself, a symphony of particles humming the same tune across billions of light years. That's not just physics, it's the universe revealing its deepest secret, that separation might be the illusion and connection the only truth. Einstein's theory of relativity and quantum non-locality seem locked in an epic standoff, two titans of physics, each brilliant, each seemingly incompatible. On one side, relativity declares nothing can outrace light, weaving space and time into an unbreakable cosmic speed limit. Information, cause and effect, even gravity itself must obey this law. Then comes quantum mechanics, where entangled particles laugh at the idea of distance, instantly mirroring each other across the universe. So who's right? Is this a battle where one theory must fall, or is there a hidden harmony waiting to be uncovered? Let's break down the conflict. Relativity isn't just about speed, it's the backbone of how we understand causality, the idea that events unfold in a logical sequence where causes always precede effects. If you could send a signal faster than light, you could theoretically message the past, unraveling the very fabric of cause and effect. That's why Einstein bristled at spooky action. It threatened to break the universe's most sacred rule. But here's the catch. Quantum non-locality doesn't actually let us send usable information faster than light. Think of it like this. Imagine you and a friend each hold one of a pair of magic coins that always land on opposite sides when flipped. You flip yours and see heads, instantly knowing theirs shows tails, no matter if they're next to you or on Mars. But here's the key, you didn't choose the outcome. You can't force their coin to land a certain way to encode a message. That's the loophole. Entanglement creates correlation, not control. The particles sync up randomly, making faster-than-light communication impossible. This subtle distinction between correlation and communication might be the bridge between relativity and quantum weirdness. Some physicists argue non-locality doesn't violate relativity because no energy or information actually travels between the particles. Instead, their connection might be written into the universe's underlying code, a pre-established harmony hidden in the math, but not everyone's convinced. Alternative interpretations like pilot wave theory suggest particles are guided by hidden forces, avoiding spooky action altogether. Others propose relativity itself might need tweaking at quantum scales, or that space-time emerges from something deeper, a quantum foam where old rules dissolve. The truth, we're still probing the edges of this paradox. Recent experiments even explore whether entanglement could stretch across time, linking particles that never coexisted. If confirmed, it would mean the universe's interconnectedness isn't just spatial, it's timeless. Until then, this clash remains one of physics' greatest mysteries, a reminder that reality might be stranger than any theory we've dreamed up. If the universe is a hologram, then non-locality isn't a bug, it's the operating system. The holographic principle, first proposed by physicist Gerard T. Hooft and later expanded by Leonard Susskind, flips our understanding of reality on its head. It suggests that everything we experience, the three-dimensional cosmos with its galaxies, black holes, and even you, might actually be a projection of information encoded on a two-dimensional surface at the universe's edge. Think of it like a movie screen. What we perceive as depth, motion, and separation could just be shadows cast by data written on a flat cosmic canvas. This isn't just a wild metaphor. The math behind black holes hints at something astonishing. Their entropy, or hidden information, doesn't scale with volume but with surface area. A black hole's event horizon, that point of no return, might be a buzzing hard drive storing all the data about what fell inside. Stretch this idea to the entire universe, and suddenly non-locality starts making eerie sense. If particles aren't truly separate but pixels on a shared screen, their instant connection isn't magic. It's like 2 points on a hologram recalculating in sync because they're part of the same underlying code. Here's where it gets mind-bending. In a holographic universe, spacetime itself could emerge from entangled quantum bits on that distant boundary. Juan Maldacner's work on anti-de Sitter space, a theoretical model of the cosmos, showed that a higher dimensional world could mathematically mirror a lower dimensional one, like a cosmic version of a Blu-ray disc holding a 3D movie. Non-locality, then, might simply be the universe reading from the same data layer. Change one entangled particle, and its partner updates instantly because they're not truly separate, just different projections of the same fundamental information. This could explain why quantum experiments keep defying classical intuition. When Aspect's photons correlated faster than light, they weren't sending signals through space, they were updating from the same source code. Even the fabric of spacetime might stitch together through quantum entanglement like threads in a tapestry. The more entangled two regions are, the closer they are in spacetime. Break the entanglement and you might sever spacetime itself, an idea that's fueling theories about wormholes and quantum gravity. So what does this mean for us? If the holographic principle holds, your sense of being a separate, isolated observer might be an illusion. The screen you're watching this on, the air you're breathing, even the thoughts in your mind could be echoes of data woven into the universe's boundary, playing out in a vast dynamic simulation. Non-locality wouldn't be a paradox, it'd be proof that we're all part of something deeper, a cosmic unity where every atom, every star, and every consciousness is fundamentally linked. The universe isn't just connected, it's a conversation, and we're all syllables in its unfolding story. What if consciousness isn't just observing reality? What if it's shaping it? This provocative idea lies at the heart of the von Neumann-Wigner interpretation, a daring twist on quantum mechanics that places human awareness front and center in the cosmic drama. Conventional quantum theory says particles exist in a haze of probabilities until measured, collapsing into definite states when observed. But here's the radical part. Von Neumann and Wigner proposed it's not machines or detectors causing this collapse, it's consciousness itself. In their view, the universe stays in a fuzzy superposition until a mind perceives it, as if reality crystallizes only when we look. This isn't just philosophical musing. Modern experiments are probing whether consciousness and quantum non-locality might be entangled in ways that defy classical logic. Take the landmark study by physicist Dean Radin in 2014. His team set up an optical system where entangled photons were observed, or intentionally ignored by human participants. The results hinted at something staggering. When people focused on the photons, their quantum behavior changed slightly, as if the act of observation subtly tugged at the fabric of reality. Skeptics dismissed it as statistical noise, but if replicated, it could mean our minds aren't passive witnesses but active players in the quantum field. Then there's the quantum Zeno effect, where observing a system frequently enough effectively freezes it in place. Apply this to consciousness, and you get a wild implication that the universe might rely on continuous observation to maintain its structure. Imagine a cosmic game of red light, green light, where particles only move when we're not looking too closely. Some theorists even speculate that without consciousness, reality might dissolve back into a sea of possibilities, a notion that blurs the line between physics and metaphysics. But how could something as intangible as consciousness influence the physical world? One clue might lie in the brain's own quantum quirks. Microtubules, tiny protein structures inside neurons, have been proposed by researchers like Stuart Hameroff and Roger Penrose as potential quantum processors, vibrating at scales where superposition and entanglement could occur. If true, our brains might be more than classical computers. They could be quantum instruments finely tuned to the universe's hidden symphony. Critics argue these ideas flirt with pseudoscience, and rightly so. Extraordinary claims demand extraordinary evidence. Yet the mystery persists. Why does quantum mechanics hinge on observation at all? Whether consciousness directly collapses wave functions or simply mirrors deeper quantum processes, the link between mind and matter remains one of science's greatest enigmas. If non-locality binds the cosmos, could consciousness be the thread that weaves it together? Until we know for sure, the universe keeps its most intimate secret that the observer and the observed might be far less separate than we think. What if nature has been using quantum non-locality all along right under our noses? While physicists debate entanglement in labs, life itself might have mastered these quantum tricks billions of years ago. Take photosynthesis, that everyday miracle turning sunlight into energy. At first glance, it's just chemistry until you zoom in. Inside plant cells, photons of light hit chlorophyll molecules, sparking a chain reaction that shuttles energy toward the reaction center. But here's the puzzle. This transfer happens with near-perfect efficiency, defying classical physics. Experiments show the energy doesn't hop randomly. It explores multiple paths at once, as if the entire system is entangled, choosing the fastest route like a cosmic GPS. This isn't just green wizardry. In 2007, researchers found evidence of quantum coherence in algae, a delicate state where molecules vibrate in sync across distances far larger than expected. It's as if the plant's energy network bypasses classical limits, tapping into non-local shortcuts to optimize every photon. Critics argue these effects are fragile, collapsing in noisy cellular environments. Yet nature seems to have cracked the code, shielding quantum states just long enough to outperform any human solar panel. If true, forests might be vast quantum computers, their leaves processing sunlight with algorithms written into the fabric of reality. Then there's the mystery of bird migration. Every year, robins and warblers navigate thousands of miles with pinpoint accuracy, guided by Earth's faint magnetic field. But here's the twist: the field is too weak for classical sensors to explain. Enter the quantum compass hypothesis. In a bird's eye, cryptochrome proteins may host entangled electrons spinning in sync with geomagnetic lines. When light hits these molecules, their quantum states shift, painting a magnetic map visible only at the subatomic level. It's like the bird sees the world through quantum-tinted glasses, perceiving forces invisible to classical systems. The wildest part, experiments with European robins suggest their navigation falters under radio waves that disrupt quantum coherence, as if jamming their internal quantum Wi-Fi. Even fruit flies, when genetically altered to lack cryptochromes, lose their magnetic sensitivity. This isn't fringe speculation. It's testable biology pointing toward quantum-assisted life. Now consider your sense of smell. Why does a molecule like limonene smell citrusy while its near-identical twin smells minty? Classical models struggle to explain this, but quantum physics might. The vibration theory proposes that odor receptors don't just detect shapes, they sense molecular vibrations through quantum tunneling, where electrons teleport across barriers to ID a molecule's unique frequency. It's as if your nose is a spectrograph reading quantum harmonics rather than static structures. Could evolution have sculpted life to exploit non-local connections? Imagine if cells communicate not just through chemical signals but through quantum links, sharing information instantly across tissues. Cancer researchers are even probing whether entanglement plays a role in DNA repair, where enzymes seem to know where damage occurs faster than diffusion allows. The implications are staggering. Biology might run on a quantum operating system we're only beginning to decode. Whether these effects are nature's clever hacks or fundamental to life itself remains open. But one thing's clear: the boundary between quantum physics and biology is blurring. If non-locality threads through living systems, it suggests a universe where connection isn't just physical but woven into the very logic of existence. From forests to migrating birds to the scent of an orange, life might be whispering quantum secrets we're finally learning to hear. What if the past isn't as fixed as we think? Quantum mechanics has already shattered our notions of space. But what about time? Enter the delayed choice experiment, a mind-bending test where particles seem to rewrite history based on decisions we haven't even made yet. Picture this: a photon approaches a beam splitter, a fork in the road where it can either go left or right. Classically, it chooses a path the moment it hits the splitter. But in the quantum world, it takes both paths simultaneously, existing in superposition until someone measures it. Now here's where time gets slippery. In a delayed choice setup, scientists wait until after the photon passes the splitter to decide whether to measure which path it took or to let it remain in superposition. Astonishingly, the photon's behavior changes retroactively, as if our future choice reaches back in time to influence its past decision. It's like mailing a letter, then deciding after it's sent whether it should arrive as a love note or a grocery list, and somehow the envelope adjusts its contents mid-flight. This isn't just theoretical sleight of hand. In 2011, physicists performed a cosmic-scale version of this experiment. They used light from distant quasars, some emitted billions of years ago, to determine measurement settings for entangled particles in a lab. The results: the particles behaved as if the quasar's ancient light knew how they'd be measured in the present, suggesting quantum correlations might thread backward through time itself. If entanglement defies linear time, what does that say about cause and effect? One radical interpretation is that time isn't fundamental, it's an illusion emerging from deeper quantum relationships. Think of reality as a tapestry where every event is interwoven, and our perception of time is just the order we happen to read those threads. In this view, the past, present, and future might all exist simultaneously, with non-locality stitching them together in ways we're only beginning to glimpse. Some theories take this further. The transactional interpretation proposes that quantum events are settled by handshakes between particles across time, with waves moving both forward and backward to finalize outcomes. It's as if the universe is a negotiation where the future influences the past as much as the past shapes the future. Even black holes might play a role. Their singularities could be knots where time's arrow frays, allowing quantum connections to loop back on themselves. The implications are staggering. If time is fluid, then free will, destiny, even memory might need redefining. Could our choices today ripple backward, subtly shaping the universe that led to us? Are we, in some faint quantum whisper, participants in a dialogue with our own past? The experiments don't just challenge physics, they invite us to reconsider what it means to exist in a universe where time might be the most flexible dimension of all. Black holes aren't just cosmic vacuum cleaners, they might be portals to a deeper layer of reality where entanglement rewrites the rules of space and time. Picture the singularity at a black hole's core, a point where gravity becomes infinite and space-time curves into oblivion. According to classical physics, anything crossing the event horizon is lost forever. But quantum mechanics paints a wilder picture. What if black holes don't destroy information? What if they rearrange it, weaving it into a web of non-local connections that span the universe? Enter the ER equals EPR conjecture, a radical idea from physicists Juan Maldacena and Leonard Susskind. This isn't just wordplay, it's a blueprint for how black holes could be cosmic hubs of entanglement. The theory proposes that entangled particles, the EPR part, might be secretly linked by microscopic wormholes, the ER part, named after Einstein and Rosen. In other words, two black holes born from the same quantum event could be connected by a tunnel through space-time, a shortcut where distance collapses to zero. It's as if the universe stitched them together with invisible threads, making them non-local neighbors despite being light years apart. Here's where it gets stranger. If you toss a book into one black hole, its information wouldn't vanish. It'd be scrambled and radiated out as Hawking radiation from both black holes simultaneously, like a cosmic Xerox machine. But here's the catch. To reconstruct the original book, you'd need access to both black holes' radiation patterns because the information is entangled across them. This isn't just storage, it's a distributed network where data exists everywhere and nowhere until someone pieces it back together. These wormholes aren't the sci-fi kind you can fly through. They're more like quantum embroidery, stitching the fabric of spacetime from the inside out. Imagine spacetime as a stretchy fabric. Poke 2 holes in it and thread a string through. That's your wormhole. Now tangle thousands of these threads between black holes across the cosmos, and suddenly the universe looks less like empty space and more like a labyrinth of hidden connections. The implications are staggering. If black holes are entangled hubs, they might be the universe's way of enforcing non-locality on a grand scale. Every time a star collapses into a black hole, it could be spinning new threads into this cosmic tapestry, weaving distant regions of spacetime into a shared quantum dialogue. Even more provocative, some theories suggest our entire universe could be inside a black hole, with its singularity birthing new universes where the laws of physics reset. In this view, black holes aren't endpoints, they're relays in a vast, interconnected network. But how do we test something so abstract? Surprisingly, labs are already simulating black hole physics using quantum computers. By entangling qubits and mimicking event horizons, researchers have observed Hawking radiation analogs, hints that black holes and entanglement are two sides of the same coin. Other teams are hunting for gravitational wave echoes, subtle ripples that could betray a wormhole's presence. If detected, it'd be smoking gun evidence that spacetime is more like a quantum net than a static stage. Whether ER equals EPR holds up or not, the idea reshapes our cosmic perspective. Black holes might not be the universe's trash cans, they could be its routers, humming with non-local traffic we're only beginning to decode. And if that's true, the darkest objects in the cosmos might also be the brightest beacons, illuminating a reality where separation is just a fleeting illusion. Dark matter might be the universe's best-kept secret, invisible, undetectable, yet holding galaxies together with its gravitational embrace. But what if its strangeness goes deeper? What if dark matter isn't just a passive scaffold but an active participant in the quantum dance, entangled across cosmic distances in ways we've barely imagined? Picture this: while ordinary matter clumps into stars and planets, dark matter could be weaving a vast, interconnected web where particles communicate instantaneously, shaping the cosmos from behind the scenes. This isn't pure speculation. We already know dark matter outnumbers visible matter 5 to 1, its gravity sculpting the universe's large-scale structure. Yet despite its dominance, it refuses to interact with light or ordinary matter except through gravity, a ghostly presence teasing us with its invisibility. But here's the twist: if dark matter particles are quantum entangled on galactic scales, their coherence could explain mysteries that baffle physicists. Take dwarf galaxies, for example. These tiny cosmic islands orbit larger galaxies like the Milky Way, but their dark matter is distributed far more smoothly than simulations predict. If dark matter were purely local, it should clump at their centers. Instead, it's as if some unseen connection keeps it evenly spread, like an invisible hand stirring a cosmic soup. Quantum coherence might offer an answer. Imagine dark matter as a superfluid, a single quantum state stretched across light years. In this scenario, particles wouldn't act independently. They'd move as a unified whole, their behavior dictated by non-local links. A tweak to one particle would ripple through the entire network instantly, maintaining equilibrium on scales that defy classical physics. This could explain why dark matter halos around galaxies stay diffuse instead of collapsing into dense cores. Their quantum nature resists the disorder that would normally pull them inward. The implications ripple outward. If dark matter is entangled, it might not just respond to gravity, it could encode it. Some theories, like Eric Verland's emergent gravity, suggest gravity itself isn't a fundamental force but a side effect of quantum information on a holographic screen. In this view, dark matter's coherence could be the substrate generating the gravitational effects we attribute to invisible mass. It's a radical idea. The extra tug we call dark matter might actually be the echo of quantum threads vibrating across the universe's hidden architecture. Could we ever detect such a quantum web? Direct observation seems impossible. If dark matter doesn't interact with light, how would we see its entanglement? But indirect hints might lurk in the cosmic microwave background, the afterglow of the Big Bang. Subtle anomalies in its polarization patterns could betray the presence of large-scale quantum correlations imprinted in the early universe. Alternatively, future gravitational wave detectors might catch whispers of dark matter particles influencing spacetime not just through mass, but through their non-local bonds. The wildest possibility, dark matter's quantum coherence might not stop at galaxies. If entanglement stretches across the cosmos, it could be the hidden framework guiding everything from galaxy clusters to the voids between them. The universe's grand design, then, wouldn't be gravity alone. It'd be gravity conducting a symphony played by quantum-entangled dark matter, a silent maestro orchestrating the cosmos from the shadows. One thing's certain, the more we probe dark matter's mysteries, the more it resembles not just a missing piece of the puzzle, but an entirely new physics, one where the quantum and the cosmic are inseparable. Whether it's a superfluid, a holographic projection, or something even stranger, dark matter refuses to fit neatly into our old models. And if its secrets are written in quantum threads, unraveling them might reveal a universe far more connected and far stranger than we ever dared to dream. Thousands of years before quantum physics entered the lab, ancient traditions were already painting a picture of cosmic connection, one that eerily mirrors our most cutting-edge discoveries. Take Indra's net, a dazzling metaphor from Buddhist and Hindu cosmology. Imagine an endless web stretching across the universe with jewels strung at every intersection. Each gem reflects all the others perfectly, creating an infinite hall of mirrors where every part contains the whole. Tweak one jewel and the entire net shimmers in response, a poetic echo of quantum entanglement where particles instantaneously mirror each other across space. The parallels don't stop there. Taoist philosophy speaks of the Tao, an indivisible flow that permeates reality, where opposites like yin and yang arise from the same source. It's a worldview that rejects separation, insisting that what we perceive as distinct entities are just temporary expressions of an underlying unity. Compare this to the quantum vacuum where particles flicker in and out of existence, their identities blurred until observation pulls them into being. Both frameworks hint at a universe where boundaries are fluid and connection runs deeper than surface appearances. In the Vedantic tradition, the concept of Brahman describes ultimate reality as a single, undivided consciousness, a cosmic ocean where individual minds are merely waves. The Upanishads declare, "Thou art that," asserting that the observer and the observed aren't truly separate. Fast forward to modern quantum interpretations like von Neumann's, where consciousness collapses wave functions and the resemblance is startling. Both suggest that perception isn't passive but participatory, weaving reality into existence through awareness itself. Even indigenous wisdom offers echoes of non-locality. The Aboriginal concept of dream time describes a realm where past, present, and future coexist, and every action ripples across time, not unlike delayed choice experiments where particles seem to retroactively respond to future measurements. The Hopi language, which lacks tenses for linear time, reflects a worldview where events are interconnected in a timeless web. What's remarkable isn't just the prescience of these ideas, it's their insistence that interconnectedness isn't abstract but experiential. Meditation practices from Zen to Sufism train the mind to dissolve the illusion of separation, accessing states where subject and object merge. Modern neuroscience now finds that advanced meditators show brainwave patterns resembling quantum coherence, their neural networks firing in synchronized harmony. Could these traditions have been tapping into non-locality through direct perception long before labs confirmed it? Skeptics argue these parallels are coincidental, that ancient metaphors are poetic, not predictive. But the overlap is too consistent to ignore. From Hermeticisms as above, so below, to the Kabbalistic tree of life mapping entangled dimensions, mystic traditions universally describe a universe far more intertwined than classical physics ever allowed. Maybe science is just catching up to a truth humans have felt for millennia. That separateness is the illusion and connection the deeper reality. Whether through meditation or particle colliders, the message is the same. We're not just in the universe, we are the universe discovering itself one insight at a time. Quantum teleportation sounds like science fiction, beaming information across distances with no physical travel. Yet this isn't Star Trek, it's real-world physics, and the breakthroughs happening today are rewriting the rules of communication. Here's how it works. Imagine you have a pair of entangled particles, say photons. These twins share a secret link, change the state of one, and the other instantly mirrors it, no matter how far apart they are. But here's the genius part. Scientists can use this link to teleport the quantum state of a third particle from one location to another without it ever moving through the space in between. The key milestone came in 2022 when researchers shattered records by teleporting quantum states across 44 kilometers of fiber optic cable, a distance spanning cities. The experiment was meticulous. One lab encoded a quantum state onto a photon, then measured it alongside one half of an entangled pair. The act of measurement triggered a change in the distant entangled partner, effectively teleporting the original state to a photon in the second lab. It's as if the information bypassed the cable entirely, hopping across the quantum link like a cosmic game of telephone. But wait, doesn't this violate relativity's cosmic speed limit? Not quite. Here's the catch. Teleportation relies on entanglement's spooky correlation, but it can't send usable information faster than light. Think of it like receiving a locked safe with no combination. The quantum state arrives instantly, but to unlock it, the receiving lab needs a classical signal sent at light speed to decode the message. Without that second piece, the teleported data is just noise. Relativity stays intact because the meaningful information still obeys the speed limit. This delicate dance has huge implications. Secure quantum networks could one day span the globe, with teleportation enabling unhackable communication. Governments and tech giants are already pouring billions into quantum internet prototypes, where data leaps between nodes without ever being vulnerable to interception. China's Micius satellite, for instance, has demonstrated space-based quantum links, teleporting states between ground stations separated by over 1,200 kilometers. Yet the most mind-bending possibility isn't just distance, it's scale. If we can teleport states between labs, could we someday teleport complex molecules or even macroscopic objects? Theoretically, yes, but the engineering challenges are staggering. Every atom's quantum state would need precise entanglement and measurement, a task exponentially harder as complexity grows. For now, we're mastering the alphabet of this new language, with entire chapters of physics waiting to be written. What's clear is this: quantum teleportation isn't magic. It's the universe revealing a hidden layer where information transcends space. And as we inch closer to a quantum internet, we're not just building faster networks. We're threading the cosmos with connections that defy everything we thought we knew about distance, one entangled photon at a time. What if non-locality isn't a feature of reality but a bug in the system? The simulation hypothesis, the idea that our universe might be an advanced digital construct, offers a spine-tingling explanation for quantum entanglement. Think of it like this: in a video game, rendering every blade of grass in real time would overwhelm even the most powerful computer. So developers use shortcuts. Distant objects share pre-programmed behaviors or pop in only when observed. Now zoom out to cosmic scales. If our universe runs on similar optimization rules, entangled particles might not be communicating faster than light. They could simply be referencing the same line of code, updating their states simultaneously because they're linked in the program's backend. This isn't just speculative fun. Modern video games already employ non-local tricks to save processing power. Take multiplayer worlds like Fortnite or Minecraft. When two players see the same tree fall on opposite sides of the map, it's not because photons traveled between them, it's because the server updates both clients instantly, syncing their realities without in-world signals. Now imagine the universe as a hyper-advanced simulation, with entanglement acting like a cosmic version of server-side scripting. Particles don't need to talk across space because their properties are determined by a deeper layer of logic outside spacetime itself. The math even hints at this. Quantum randomness, the unpredictable behavior of particles, mirrors the pseudo-random number generators used in software. And wave function collapse, that could be the universe's render-on-demand feature, where quantum states only solidify when observed to conserve computational resources. Even the holographic principle, with its suggestion that reality is a two-dimensional projection, fits eerily well with how graphics engines construct three-dimensional worlds from flat texture files. But here's the twist. If non-locality is a rendering glitch, it might leave detectable fingerprints. Physicists like Seeler's Bean propose that simulated universes would have energy limits cutoffs in high-energy particle behavior, like a pixelated screen revealing its resolution under a microscope. Others suggest that quantum randomness might not be perfectly smooth, containing statistical anomalies akin to the subtle patterns in computer-generated random numbers. Of course, calling reality a simulation doesn't answer the ultimate question. It just kicks it upstairs. Who or what runs the program, and is their universe real, or another layer in an infinite stack of simulations? Either way, non-locality's eerie efficiency, its refusal to play by classical rules, makes a strange kind of sense if spacetime is just the user interface of something far deeper. Whether the universe is code or consciousness, pixels or particles, one thing's clear: the connectedness we're uncovering isn't just a feature of reality. It might be the signature of its source. The idea that our thoughts or intentions could influence someone's health from across the room, or even across the world, sounds like pure fantasy. But what if quantum non-locality, that same spooky connection binding particles, also threads through living systems? This is the controversial frontier of non-local healing, where claims range from the tantalizing to the outright absurd. On one end, you've got charismatic gurus selling quantum energy bracelets and weekend workshops promising to cure diseases with vibes. On the other, rigorous studies, some funded by the National Institutes of Health, exploring whether focused intention can measurably affect biology at a distance. So where's the line between wishful thinking and something deeper? Let's start with the most scrutinized claim: distant healing intention. In the lab, experiments have tested whether healers, often trained in practices like Reiki or Qigong, can influence living systems without physical contact. One study published in the Journal of Alternative and Complementary Medicine found that trained practitioners could alter the growth rate of cancer cells in a petri dish from another room, with no known mechanism to explain the effect. Skeptics dismissed it as flawed methodology, but similar results have popped up in studies on wound healing in mice and even human heart rate variability. The common thread: when intention is directed with precision, some biological systems seem to respond, as if the healer and subject are momentarily entangled. Then there's the infamous Maharishi effect, a phenomenon where large groups meditating together reportedly lowered crime rates in nearby cities. Critics argue these studies cherry-pick data, but meta-analyses of dozens of trials suggest a small but persistent correlation between collective intention and reduced violence. It's a fringe idea, but if quantum non-locality connects particles, could it also link minds on a societal scale? The Institute of Noetic Sciences has spent decades probing this with mixed but intriguing results. But here's the catch: for every study hinting at non-local effects, there's a mountain of pseudoscience muddying the waters. The term quantum healing has been hijacked by marketers peddling everything from magnetic pillows to frequencies that claim to rebalance your DNA. Real quantum biology, like photosynthesis harnessing coherence, operates at scales and conditions wildly different from a weekend workshop's chance. The danger isn't just bad science, it's diverting patients from evidence-based medicine with false promises. So how might genuine non-local healing work if it exists? One theory points to the body's biofield, an electromagnetic network some researchers believe coordinates cellular communication. Studies show cells emit photons in patterns that shift during illness, suggesting a light-based language we barely understand. If entanglement plays a role, could focused intention act like a tuning fork, nudging this system toward harmony? It's a stretch, but not impossible. After all, if birds navigate via quantum spins, why couldn't our own biology have subtle quantum layers? The truth is, we're still at the dawn of unraveling these mysteries. What's clear is this: the universe's interconnectedness doesn't grant magical healing powers, but it might hide subtle channels we're only beginning to map. Until then, the best prescription is equal parts open-minded curiosity and razor-sharp skepticism, because in the quantum realm, the line between miracle and mirage is thinner than we think. Imagine a future where sensitive data, bank transactions, medical records, military communications travels via a network so secure that hacking it would be as futile as trying to catch smoke with your hands. This isn't science fiction, it's the vision behind the quantum internet, a revolutionary leap in global connectivity powered by the same spooky entanglement that baffled Einstein. Unlike today's fiber optic networks where data can be intercepted and copied, a quantum internet would use entangled particles to create unbreakable encryption keys, rendering eavesdropping physically impossible. The secret lies in the fundamental rule of quantum mechanics: measuring a particle alters its state. Any attempt to spy on a quantum-encoded message would immediately corrupt it, leaving a glaring fingerprint of tampering. China's Micius satellite already blazed a trail in 2017, demonstrating entanglement distribution over record-breaking distances. Beaming entangled photon pairs to ground stations 1,200 kilometers apart, it proved that space-based quantum links could survive the brutal journey through Earth's atmosphere. Meanwhile, under Chicago's streets, a 52-mile quantum loop snakes through Argonne National Laboratory, testing how entangled photons fare in real-world fiber optic cables. These projects aren't standalone experiments, they're the first nodes in a coming quantum web, where satellites and underground fibers form a hybrid backbone for unhackable communication. But building this network isn't as simple as swapping classical routers for quantum ones. Entanglement is notoriously fragile, crumbling when exposed to heat, vibration, or even stray magnetic fields. To overcome this, engineers are designing quantum repeaters, devices that extend entanglement's reach by stitching together shorter links into a seamless chain. Picture a relay race where each runner passes a baton without ever touching it. Quantum teleportation techniques allow entangled states to hop between nodes, healing breaks in the network without losing coherence. Early prototypes in Delft and Vienna have successfully teleported states between non-adjacent nodes, proving the concept scales beyond lab benches. The stakes couldn't be higher. A functional quantum internet wouldn't just protect data, it would enable breakthroughs we can barely envision. Imagine scientists collaborating with perfectly synchronized atomic clocks, creating telescopes with Earth-sized resolution, or simulating complex molecules for drug discovery by linking quantum computers across continents. Governments recognize the potential. the US Department of Energy mapped a blueprint for a national quantum network, while the European Quantum Internet Alliance aims to connect 10 cities by 2030. Yet the grandest ambition lies in uniting these fragments into a planet-spanning lattice. Some propose a constellation of quantum satellites orbiting hubs that distribute entanglement like celestial switchboards. Others envision fiber optic arteries reinforced with quantum memory crystals, storing fragile states long enough to bridge continents. Whichever path wins, the result will be a communication revolution, not faster but fundamentally different. For the first time in history, privacy wouldn't rely on math problems hackers might one day solve, but on the unbreakable laws of physics themselves. The quantum internet isn't just a new way to send messages, it's a rewrite of the rules, turning the universe's spookiest phenomenon into humanity's most secure handshake. Non-locality isn't confined to labs and equations. It's been seeping into art and culture for decades, whispering through films, music, and literature like a hidden pulse. Take Christopher Nolan's Interstellar, where the climactic tesseract scene bends spacetime into a mind-bending library. Cooper, stranded in a higher dimension, peers through the fabric of time, seeing his daughter's past as a physical space he can touch. It's a visual metaphor for quantum entanglement's eerie connectivity, where love and gravity transcend dimensions, a Hollywood blockbuster riffing on the same physics that makes Einstein's spooky action so unsettling. Then there's Björk's Biophilia, an entire album structured around cosmic phenomena. In crystalline, chaotic percussion mimics electron orbits, while Mutual Core uses seismic beats to echo tectonic shifts, sonic nods to how particles influence each other across voids. But the real marvel is hollow, where Theremin's wavering pitch mirrors quantum uncertainty, and the music video plunges into fractal patterns that evoke entangled webs. Björk didn't just sing about nature, she encoded non-locality's rhythms into the music itself, turning songs into vibrating strands of a larger quantum tapestry. Literature, too, has danced with these ideas. Philip Pullman's His Dark Materials trilogy imagines dust, a mysterious particle bridging consciousness across parallel worlds. Just like entangled photons, dust responds to human awareness, binding Lyra's fate to wills despite their separation by universes. Pullman's genius was wrapping metaphysics in fantasy, making entanglement feel as tangible as a child's intuition. Even earlier, Jorge Luis Borges wrote The Garden of Forking Paths, a labyrinthine story where every decision splinters reality into parallel timelines, a literary precursor to the many worlds interpretation of quantum mechanics. Visual artists aren't far behind. Tokyo's Team Lab Collective crafts immersive digital installations where flowers bloom under visitors' footsteps, then scatter their petals to influence blooms in another room. Walk through their universe of water particles exhibit, and you'll see waves ripple across walls in real time, responding to unseen hands continents away, a poetic echo of non-local connection. Meanwhile, sculptor Antony Gormley's Quantum Cloud series turns human forms into shimmering constellations of steel rods, as if the body itself is a probability wave waiting to collapse. What ties these works together? A shared intuition that reality seems are softer than we think. Whether through Nolan's Tesseract or Björk's quantum soundscapes, artists keep circling back to the same truth physicists are now proving. That separation might be a trick of perspective and connection, the deeper law. In a world obsessed with boundaries, art reminds us, sometimes screaming, sometimes whispering, that we're all threads in the same vibrating web. Could the universe itself be conscious, not in the way we typically think of consciousness, no brain, no neurons, but something far more fundamental, woven into the fabric of reality itself? This is the radical proposition of panpsychism, the idea that consciousness isn't a latecomer to the cosmos but a foundational feature, present even at the level of subatomic particles. And when you pair this with quantum non-locality, things get even stranger. If particles can instantaneously influence each other across vast distances, could that interconnectedness hint at a deeper, universal awareness, a cosmic mind humming beneath the surface of reality? One of the boldest voices in this space was physicist David Bohm, who saw non-locality as a clue to a hidden order beneath the chaos. Bohm's implicate order theory suggests that what we perceive as separate objects, tables, stars, even our own bodies, are just temporary unfoldings of a deeper, enfolded reality. Imagine dipping a piece of paper into ink, then folding it over and over until the stain vanishes from view. To us, the ink seems gone, but it's still there, hidden in the creases. Bohm argued that particles are like those ink stains, apparently separate on the surface, but fundamentally unified in the implicate order. Their entanglement isn't a quirk, it's a glimpse of this underlying wholeness. Even more intriguing, Bohm believed this hidden order might be mental as much as physical. He proposed that consciousness and matter are two sides of the same coin, with the implicate order acting as a kind of cosmic medium where thought and reality intertwine. In this view, when we observe a particle and collapse its wave function, we're not an outsider affecting the system. We're part of the same unfolding process, a ripple in a vast conscious ocean. Panpsychists take this further, arguing that if even atoms have a rudimentary form of experience, what philosopher Alfred North Whitehead called proto-consciousness, then entanglement might be how these tiny whispers of awareness communicate. Think of a murmuration of starlings where thousands of birds move as one, responding instantly to unseen cues. No central leader calls the shots. Instead, each bird's tiny awareness links into a larger, emergent intelligence. Could entangled particles be doing the same, their micro-experiences combining into something grander? The implications are staggering. If panpsychism is right, then the universe isn't just a collection of dead matter obeying blind laws. It's a dynamic, self-aware network where every quark, every galaxy participates in a shared experience. This isn't mysticism, it's a serious philosophical stance gaining traction in consciousness studies. Neuroscientist Christoph Koch, once a skeptic, now argues that integrated information theory, a framework for measuring consciousness, suggests even simple systems might possess tiny degrees of experience. Critics, of course, dismiss this as poetic speculation. How could atoms feel anything, and if everything is conscious, why doesn't my toaster write poetry? But panpsychists counter that consciousness isn't binary on or off, but a spectrum. A rock's experience wouldn't resemble human thought any more than a single pixel resembles a movie. Yet combined, those pixels create meaning. Similarly, if the universe is a vast quantum network, its collective mind might be less like a human ego and more like a cosmic dream, with entanglement as the thread stitching it all together. Whether panpsychism holds up or not, it reframes non-locality as more than just physics. If particles are linked not just by forces but by something akin to shared experience, then reality might be far more alive, far more connected than we ever imagined. The next time you look at the night sky, consider this: those distant stars aren't just balls of gas. They might be participants in a silent, universal conversation, one we're only beginning to hear. What if an object could dance to a rhythm older than time itself? Time crystals aren't science fiction. They're a bizarre new phase of matter that defies the ordinary laws of physics. Unlike everyday crystals where atoms arrange themselves in repeating patterns in space, time crystals tick through cycles in time, returning to their initial state like a cosmic metronome with no energy input. And here's where it gets weirder. These structures might hold the key to seeing non-locality unfold in 4 dimensions, blending space and time into a single, entangled tapestry. The idea of time crystals first emerged in 2012 when Nobel laureate Frank Wilczek theorized a system that breaks time translation symmetry, a fancy way of saying it can't sit still, even in its lowest energy state. At first, physicists dismissed it as impossible, a violation of thermodynamics. But by 2017, two independent teams had created time crystals in the lab, using chains of ytterbium ions and nitrogen vacancies in diamonds. These weren't just curiosities, they were the first examples of matter perpetually in motion without energy loss, like a clock that ticks forever without winding. Then came the quantum computing revolution. In 2021, researchers at Stanford and Google Quantum AI engineered time crystals inside their quantum processors using qubits as the building blocks. They fired a sequence of laser pulses at the system, not to drive it but to reveal its intrinsic rhythm. Remarkably, the qubits synchronized into a stable pattern, flipping back and forth between states in a perfect loop, a signature of time crystalline order. But the real shock was this: the crystal's behavior seemed to correlate across the entire processor instantaneously, as if the qubits were entangled not just in space but in time. This is where non-locality enters the fourth dimension. In a normal crystal, shaking one atom affects its neighbors through physical proximity. But in a time crystal, disturbing one qubit could ripple through the system's entire history and future, a kind of temporal entanglement. Picture throwing a pebble into a pond and watching the splash echo backward through time as well as outward across the water. Experiments suggest these crystals might encode information in their repeating cycles that's accessible at any point in the sequence, meaning the past, present, and future states could be fundamentally linked, like pages in a book that rewrite each other as you read. The implications are staggering. If time crystals can sustain non-local correlations across time, they might offer a blueprint for quantum memory that's immune to decay, a storage system where data isn't just preserved but renewed with every tick of the crystal's clock. Some theorists even speculate they could model closed time-like curves, hypothetical loops in spacetime that flirt with time travel. And because time crystals are inherently out of equilibrium, they might reveal new phases of matter that only exist in the quantum realm, where the usual rules of cause and effect start to bend. What's next? Labs are racing to scale up these experiments, aiming to create larger, more stable time crystals that could one day power fault-tolerant quantum computers or probe the boundary between quantum mechanics and gravity. But even in their current, fragile state, they're teaching us something profound, that the universe's interconnectedness might not be limited to space. If particles can whisper across galaxies, why not across seconds, years, or eons? Time crystals aren't just a new material, they're a window into a reality where time itself might be just another thread in the quantum web. The biggest rift in physics isn't between theories, it's between worlds. On one side, quantum mechanics rules the microscopic realm with probabilities and entanglement, where particles flicker in and out of existence and space is a seething foam. On the other, Einstein's general relativity governs the cosmos, painting gravity as the smooth curvature of spacetime, where planets and black holes move with clockwork precision. For a century, these titans have refused to speak the same language, each flawless in their domain yet mutually unintelligible. But what if non-locality, that eerie quantum thread connecting particles instantly, is the Rosetta Stone we've been missing? Loop quantum gravity takes the first daring step, proposing that spacetime isn't continuous but woven from tiny, indivisible loops. Picture the universe as a cosmic mesh, each thread a vibrating strand of Planck-length scale. These loops don't exist in space, they are space, knotting together to form the fabric of reality. Now here's where non-locality enters. Just as entangled particles ignore distance, these loops could link disparate regions of spacetime, creating shortcuts where gravity emerges from their quantum tangles. In this framework, a black hole's singularity isn't a point of infinite density, but a nexus where loops tangle so tightly they rewrite the rules of proximity. Two distant loops entangled at birth might still feel each other's twists across cosmic epochs, making gravity a holographic illusion, a force that seems local but is actually stitched together by non-local quantum threads. String theory dances to a different but equally radical tune. Here, the fundamental units aren't loops but vibrating strings, each oscillation producing a different particle. To reconcile gravity with quantum mechanics, strings need extra dimensions, tiny, curled-up spaces hidden from our perception. Non-locality sneaks in through the holographic principle, where a string's vibration in higher dimensions can instantaneously affect its shadow on a lower dimensional boundary. Imagine plucking a guitar string in 5 dimensions and hearing the note echo in our 3-dimensional world with no delay. This isn't magic, it's the universe running on quantum code, where entanglement bridges dimensions. The most provocative fusion comes from ER equals EPR, the idea that entangled particles EPR might be connected by microscopic wormholes If true, every quantum connection could be a tunnel through space-time, making non-locality the glue holding the universe's geometry together. Black holes, often seen as gravity's ultimate triumph, might actually be quantum entanglement writ large, their event horizons acting as cosmic hard drives where information is stored non-locally, escaping the classic fate of being lost forever. Recent simulations on quantum computers have shown tantalizing hints of this, with entangled qubits mimicking wormhole dynamics, as if the universe's 2 great theories were secretly collaborating behind the scenes. Yet the puzzle isn't solved. Critics point out that neither loop quantum gravity nor string theory has produced testable predictions to crown one as the victor. But non-locality offers a clue. If spacetime itself is built from quantum connections, then probing entanglement at larger scales, say, with space-based experiments linking satellites and quantum memories, might reveal gravity's quantum roots. Some even speculate that dark energy, the mysterious force accelerating the universe's expansion, could be non-locality's long-range whispers, a relic of primordial quantum links stretched to cosmic scales. The stakes couldn't be higher. Unifying these theories wouldn't just satisfy physicists, it would rewrite our origin story. Was the Big Bang a quantum fluctuation in a deeper, non-local network? Is the arrow of time just entanglement's echo? Every experiment peeling back non-locality's layers brings us closer to an answer, one that might finally show us the universe isn't held together by forces but by conversations, an infinite dialogue spanning every dimension, every moment, every possible world. Entanglement swapping sounds like something out of a heist movie, a stealthy handoff of quantum secrets between particles that never even met. But this isn't fiction. It's one of the most mind-bending experiments in physics, proving that quantum connections can leapfrog across the cosmos like whispers passed through a chain of strangers. Here's how it works. Imagine you have 2 pairs of entangled particles. Let's call them pair A and pair B. The particles in each pair are linked, but the pairs themselves have no direct connection. Now bring 1 particle from each pair together in a lab and perform a special measurement called a Bell state measurement. The magic happens instantly. The remaining 2 particles, the ones you didn't touch, now separated by vast distances, suddenly become entangled as if they've been linked all along. It's like introducing 2 friends at a party and watching their other friends, miles apart, suddenly start finishing each other's sentences without ever speaking. This isn't just a neat trick, it's a loophole in how we understand causality. In 2012, a team led by Anton Zeilinger demonstrated entanglement swapping over 143 kilometers between the Canary Islands using photons sent through the open air. The experiment confirmed that quantum links don't need physical proximity or even a shared history. The particles that ended up entangled had never interacted. Their bond was forged purely through the act of measuring their partners. It's as if the universe has a hidden switchboard, rerouting connections on the fly without regard for space or time. The implications are staggering. If entanglement can hop between particles like this, it suggests the universe might be crisscrossed with a dynamic quantum web, where connections form and reform in real time. Picture a cosmic game of telephone, where the message isn't passed step by step but teleports directly to the end of the line. This could revolutionize quantum networks, enabling secure communication between nodes that have no direct link, just a chain of swapped entanglements bridging the gap. But the real jaw-dropper, entanglement swapping, might hold clues to quantum gravity. Some theorists propose that spacetime itself emerges from these cascading quantum connections, like a 3D hologram projected from entangled data on a 2D surface. If swapping can create entanglement across arbitrary distances, it could mean the fabric of reality is constantly rewiring itself beneath our feet, stitching together new threads in the cosmic tapestry. Critics argue these ideas are speculative, and they're right. We're still piecing together the rules, but labs worldwide aren't waiting. China's Micius satellite has already tested swapping in orbit, and startups are racing to build quantum repeaters that use swapping to extend entanglement across continents. Whether it's for unhackable networks or probing the nature of spacetime, one thing's clear: entanglement swapping isn't just linking particles. It's showing us that the universe might be far more fluid, far more connected than we ever dared to dream. If quantum non-locality reveals that every particle in the universe is silently entangled, that the flutter of a butterfly's wing might ripple across galaxies, then shouldn't our ethics evolve to match this radical interconnectedness? Consider the implications. If actions taken in one corner of the cosmos can resonate instantaneously elsewhere, even in ways we can't yet measure, then the old boundaries of responsibility start to crumble. We're no longer isolated actors in separate domains, but participants in a vast dynamic web where every choice sends tremors through the whole. This isn't just metaphysics, it's a challenge to rethink everything from environmental policy to social justice. Take ecology. Traditional conservation focuses on local systems, protecting a forest here, a river there. But if ecosystems are quantum entangled at some fundamental level, then poisoning a watershed or clear-cutting a jungle might have non-local effects we've never accounted for. Could dying coral reefs be subtly influencing soil microbes a continent away? It sounds absurd, yet if particles defy classical limits, why not ecosystems? Philosophers like Alain Aspect championed deep ecology, arguing that all life has intrinsic value. Now, quantum biology hints there might be literal, physical threads binding that value together. Imagine a quantum stewardship ethic where polluters aren't just fined for local damage, but held accountable for destabilizing the planet's hidden quantum coherence. The social sphere is equally fraught. Studies in collective consciousness like the Maharishi effect suggest group meditation might lower crime rates in distant cities. While skeptics dismiss this as coincidence, if non-locality operates at macroscopic scales, could hatred or compassion ripple through societies like entangled photons? History is littered with examples of cultural shifts spreading inexplicably fast: the fall of the Berlin Wall, the Arab Spring. What if these weren't just chain reactions but quantum-like phase transitions, where collective intention tunnels through barriers as if they weren't there? Ethical systems built on individualism would need radical overhauls. Privacy laws, for instance, might struggle with the idea that thoughts or emotions could have measurable effects beyond the brain, blurring the line between personal and collective accountability. Even technology's trajectory would shift. Social media algorithms already exploit our neural vulnerabilities. What if they tapped into non-local resonance, amplifying discord or solidarity at scales we can't perceive? A tweet inciting violence might carry hidden quantum weight, its impact magnified by entanglement we don't yet understand. Conversely, could platforms designed to foster empathy harness non-locality to heal divides? The moral burden on tech giants would skyrocket if their tools weren't just shaping minds but the fabric of shared reality itself. Critics will argue this is a slippery slope, that without empirical proof of macroscopic entanglement, we risk basing ethics on speculative physics. But climate science once faced the same skepticism. If we'd acted earlier on weaker evidence, today's crises might be less dire. the precautionary principle acting to prevent harm even without full certainty, could demand we err on the side of quantum caution. After all, if non-locality teaches anything, it's that separation is an illusion. The old ethics of out of sight, out of mind no longer hold. Every decision, from recycling a soda can to launching a war, might echo in ways we're only beginning to glimpse. The choice is stark: cling to a world view where things are separate and controllable, or embrace one where every act is a pebble dropped into a cosmic pond. The ripples, it seems, are everywhere. What if we could predict earthquakes before the ground even trembles, or peer into the void to catch dark matter red-handed? The next revolution in sensing technology won't rely on brute force precision, but on the universe's own ghostly wiring, quantum entanglement. Imagine sensors so sensitive they detect disturbances in the fabric of space-time itself, not by measuring force or light, but by reading the silent whispers between entangled particles. Take quantum radar, a breakthrough already leaping from theory to prototype. Traditional radar bounces radio waves off objects, but quantum radar exploits entangled photons. One photon stays in the lab while its twin is fired into the field. Any disturbance, a stealth aircraft, a buried mineral deposit, alters the traveling photon, and its entangled partner feels the change instantly, even before the signal could physically return. Early tests in 2023 showed unprecedented resolution, spotting objects conventional systems missed entirely. Now, scale this idea to seismic sensors. Entangled atoms in underground arrays could act as ultra-sensitive strain gauges, detecting subtle shifts in tectonic plates days before traditional seismometers register a blip. The particles wouldn't just measure movement, they'd anticipate it, their non-local links offering a real-time snapshot of Earth's hidden stresses. But the real game changer: dark matter hunting. Despite making up 85% of the universe's mass, dark matter barely interacts with ordinary matter. Current detectors wait years for a single collision in vats of xenon or silicon. Quantum sensors flip the script. Proposals like the Quantum Entanglement Enhanced Detector (QED) use entangled nuclei as dark matter microphones. When a dark matter particle grazes one nucleus, its entangled partner vibrates in sync, amplifying the signal like a quantum version of noise-canceling headphones. It's not about brute force collisions anymore, it's about listening to the universe's faintest hum through particles that dance in lockstep across distances. Even medical imaging stands to transform. MRI machines today require massive magnetic fields and cryogenic cooling. Quantum-entangled biosensors could track neural activity or blood flow at the cellular level with zero invasive scanning. Picture a wearable patch that monitors your brain's quantum spin states, diagnosing strokes or tumors before symptoms appear, all because entangled electrons in the device relay changes faster than any classical signal could. The catch: these technologies demand quantum coherence at scales and durations we're still mastering. Labs are racing to engineer materials that protect entanglement from heat and noise, like diamond lattices with built-in nitrogen vacancies. Yet the potential is too staggering to ignore. From earthquake-proof cities to telescopes that see the invisible, non-local sensors don't just push boundaries, they erase them, turning the universe's spookiest phenomenon into humanity's sharpest tool. The Pentagon's recent declassified reports on UAP's unidentified aerial phenomena read like a sci-fi novel, but the physics behind them might be even stranger. Among the wildest theories circulating in defense and scientific circles is the idea that some UAPs don't fly through the air so much as cheat space itself, leveraging quantum non-locality to bypass conventional propulsion. Forget rocket fuel. What if these crafts are tapping into the fabric of reality, bending entanglement and vacuum energy to leap across skies, oceans, even dimensions? At the heart of this speculation is the concept of quantum vacuum engineering. The vacuum of space isn't empty, It's a seething ocean of virtual particles popping in and out of existence, a phenomenon known as zero-point energy. Some physicists, including those advising the Pentagon's Advanced Aerospace Threat Identification Program, theorize that an ultra-advanced propulsion system could manipulate this quantum foam, creating localized distortions that allow for instantaneous acceleration or even apparent teleportation. Imagine a craft that doesn't push against air but pulls on space-time itself, like a surfer riding a wave of entangled particles. The link to non-locality comes in when you consider how such a system might navigate. If entanglement connects particles across arbitrary distances, a vehicle exploiting this could know the state of its destination before arriving, adjusting its trajectory not through aerodynamics but through quantum correlations. Reports from Navy pilots describe UAPs executing maneuvers that defy inertia, sudden 90-degree turns at hypersonic speeds, abrupt stops with no deceleration burns. Classical physics screams in protest, but quantum mechanics whispers, what if these objects aren't fighting gravity but sidestepping it entirely? Even the Pentagon's language hints at this. Their 2021 report explicitly mentions breakthrough technologies that could explain UAP capabilities, with classified annexes rumored to delve into quantum propulsion. While no smoking gun has emerged, patents filed by aerospace contractors like Salvatore Pais describe hybrid aerospace undersea craft using inertial mass reduction, a euphemism some speculate for bending spacetime via quantum effects. Skeptics dismiss Pais's work as speculative, but the Navy's patent approval and subsequent research grants suggest serious interest. The most tantalizing and controversial evidence comes from incidents like the 2004 Nimitz encounter. Pilots tracked a UAP dubbed the Tic Tac, descending from 80,000 feet to sea level in seconds, a feat requiring accelerations that would vaporize any known material. Radar operators reported the object appearing simultaneously in multiple locations, a glitch unless you consider quantum superposition. Could the Tic Tac have been exploiting non-local links to exist in several places at once, collapsing its position only when observed? Of course, the leap from quantum theory to functional UAPs is vast. Lab experiments with entanglement are fragile, requiring near absolute zero temperatures and painstaking isolation from noise. Scaling this to a vehicle that operates in Earth's atmosphere seems absurd unless an unknown civilization cracked the puzzle millennia ago. Ancient astronaut theorists jump on this, pointing to historical accounts of celestial chariots performing impossible maneuvers. Mainstream science rolls its eyes, but the Pentagon's continued funding into quantum vacuum research suggests the question isn't as outlandish as it seems. Whether UAPs are alien, secret tech, or natural phenomena misperceived, their study is forcing us to confront a startling possibility: that the universe's rulebook allows for feats we've barely begun to imagine. If non-locality can stitch together particles across galaxies, who's to say it couldn't power a craft that defies every textbook on aerodynamics? Until we know for sure, the skies remain a theater of mysteries, and quantum physics might hold the script. From entangled particles whispering across galaxies to time crystals ticking in perfect sync with the past and future, we've seen how non-locality shreds every boundary we once took for granted. Space just a stage where quantum actors ignore the script. Time more like a tapestry where threads from different eras knot together unseen. Even consciousness, that flickering flame of awareness, might not be locked inside our skulls, but a ripple in a vast, interconnected field of perception. The universe isn't just a collection of separate things. It's a dynamic conversation where the participants are linked in ways that defy distance, duration, and perhaps even individuality. Think of the implications. When you touch a tree, you're not just making contact with bark and leaves. You're interacting with a network of atoms that might still be entangled with stardust from the birth of the cosmos. When you remember a childhood moment, those neurons firing in your brain could be echoing patterns woven into the fabric of space-time itself. And when you feel a sudden connection to someone miles away, it might not just be intuition, it could be the universe's hidden threads pulling taut between you. This isn't mysticism, it's the frontier of science where lab results keep confirming that reality is far stranger than our ancestors, or even Einstein could have imagined. Whether it's black holes connected by wormholes or dark matter humming in quantum harmony across the void, the message is the same: separation is an illusion. The deeper we probe, the more the universe reveals itself as a single, shimmering whole, one where every part reflects every other, like jewels in Indra's net. Carl Sagan once said, "We are a way for the cosmos to know itself." Now we see how literal that might be. If non-locality binds everything from particles to galaxies, then gazing at the night sky isn't just observation, it's the universe gazing back through your eyes. Every question we ask, every experiment we run, is the cosmos unraveling its own mysteries using minds it grew for the purpose. So the next time you feel small under the stars, remember, you're not just in the universe. You are the universe thinking, feeling, discovering its own boundless connections. And if that doesn't change how you move through the world, nothing will.